We're kicking off this semester's sessions of the IDSS Distinguished Speaker Seminar Series. It's really my pleasure to have Hamsa Bastani, who's joining us from UPenn Wharton. I guess I have known a lot of her work on sequential decision making and really using techniques that you often see in such theoretical settings like bandits and active learning, actually applied in the field, like, I don't know, assisting the Greek government in making consequential immigration decisions. But I think she's going to talk about some other work related to the winner's curse. So let's welcome Hamsa.
So thanks, Dean, and thank you guys for having me here. Thanks for making it out at 4 p.m. on a Tuesday when I'm sure you'd rather be getting coffee somewhere. I'll be talking about some joint work with Osbert Bastani, who's at Penn CS and also works as my husband, and co-author's main job. And then Bryce McLaughlin, who is a postdoc who will be heading to BC. So he's coming to Boston, so look him up if you guys are staying here. He's absolutely fantastic. And I'd love to keep it as conversational as possible, so feel free to jump in with any questions, comments, thoughts, random feelings, sure. Okay, so we got interested in this problem pretty recently because there's been a huge surge of interest generally about making data-driven decisions, especially in my field, operations management, but also in marketing and econ and a lot of other adjacent fields. What is data-driven decision making is kind of broad, so I just wanted to make it clear. Usually you have some covariates X that you're observing, some treatments T. This could be anything, whether it's you're targeting interventions to patients or discounts to customers, or even the running example I'm going to use is matching refugees to cities. So the treatments there are locations, and then there's some outcome. It could be profit, social welfare, whatever you're interested in. And typically, we assume, or authors assume, that the treatments are assigned randomly or as if randomly, and there's no unobserved confounding. And so what do? First, you estimate some kind of rich predictive model. This could be parametric, non-parametric, that tries to take the covariates and the treatments and fits the outcome Y. Now you try to learn a targeting policy. So you optimize pi hat of X. So you're saying for this particular person, they should get this treatment T, right? And that's a targeting policy. So that's me saying, oh, these patients should get this intervention, or these refugees should go to these cities, right? And then when you try to communicate this to any stakeholder or decision maker, you need to evaluate the policy. So you need to say, I think this policy pi hat that I learned is going to do this much better than whatever you're doing right now, right? So like I said, as a running example, I'm going to use this data-driven refugee integration paper, which made a huge splash, and it was a very impressive effort. This was published in 2018 in Science. Interestingly, there was concurrent work by an OR, totally different team, published in Operations Research, obviously much later because our review process is way slower, but I understand that they were concurrent. And so basically what both papers independently came up with is we can take refugee-level covariates, like their education and whether or not they speak English and things like that, and predict how well they're going to be employed at every possible city that a refugee could be placed in. And there's about 50 cities that we're talking about. So they're fitting like 50 different models, right? And then we're going to solve this big optimization problem to decide where to send each refugee. So just to put this in like mathematical notation, we have refugee attributes. We have the treatments are the placement locations they're going in. Unfortunately, there's not a lot of appetite for refugees in the United States, and so they have capacity constraints and they are binding. So it's not like we can send more people to a location or anything like that, but we can shuffle them around in a data-driven way. Y is the 90-day employment outcome. That's the outcome that they track, and for whatever reason is the one they're interested in, right? And we think that, if people get employed, they're more likely to get integrated into the community and the social fabric and thrive, right? And the goal is to learn a policy to take these refugee-level features and map them to cities in order to maximize the total employment outcomes, right? So what do? They do exactly the pipeline I just mentioned. So first you train a predictive model predicting using refugee level features and city level location features, the city level attributes to predict employment. Then you obtain a policy where you take the argmax of this employment outcome, right? And you match refugees to locations subject to some capacity constraints. So this is like an IP, an integer program. And then the question is, how do you evaluate it, right? So Marze came to Boston. We don't know how Marze would have done in Philadelphia. I think great, but we don't know, right? And so a reasonable surrogate is, okay, well, I trained this fancy predictive model. I checked it out of sample. It predicts well. So you know what? I'm just going to use that predictive model to give me the counterfactual. And then I evaluate the sum. So this is a very, very common strategy in the literature. So I'll show you a literature survey in a little bit. But it estimates, 20 to 75% improved employment. So this was like a huge effort, and across both teams, they found the same kind of large effect sizes. I'm going to argue that this is not a valid strategy to do policy evaluation, right? Because of something called the winner's curse, right? So let's say that this is our true model. It's like the solid line over here, where the y is the outcome and the x-axis is like whatever treatment that you like, right? And this green star is the maximizer, right? We fit some predictive model. It's always noisy. Hopefully it's an unbiased estimate. So let's say we fit this like dashed line. As we're moving towards more and more fancier machine learning models, it's more likely that it's kind of all over the place because it's non-parametric. This model on its own is actually a pretty good predictor. But when we take the max of this predictor, we get this curve. And so the winner's curse is that I'm going to use this guy to evaluate how well this decision is. And the true value of the decision is down here. So this gap is really what's called the winner's curse. It's sort of my post-decision disappointment. So winner's curse actually originates from auction theory, where let's say that we have a common value auction. We're all thinking about the same phone or something, or coffee, and we each get, those are totally different things. So we each get an unbiased sample of the value of this item, and then the person who wins had the maximum value, and that's obviously going to be an overestimate in expectation compared to the true value, right? Does that make sense? Okay. Emily's my nodder. It's great to have a nodder. Okay, so what we did was we set up a realistic simulation where we just looked at the supplementary material. We took the sample sizes. We took the same marginal distributions. And we set up an environment. But importantly, we decided that we would create a null effect environment. So basically, in this setting, refugee level characteristics are predictive of treatment. Predictive of outcomes. And the city you get placed in is also predictive of outcomes because some cities just cater much better. But we made sure there are no refugee location interaction effects. So this means that you can shuffle people around as much as you want. You're not going to change the overall employment outcomes because some cities are better, some people are better at getting employed, but there's no value to any data-driven matching, right? And we find that if you actually run their policy evaluation procedure, you still get this 60% estimate. So this pink histogram over here, evaluated over many draws of the data, many evaluations, and so on. And you can see it's fairly tightly concentrated. So very systematically, we're thinking we can do 60% better, even though the ground truth is that there's nothing you can do. This is an inverse propensity weighting, probability weighting kind of approach where we use a held-out test set and we do IPW. Like I'll mention later, this is a model-free method, and indeed it's very high variance, but it predicts that the mean effect is 0. Right? So when we talked to people about this, they said, well, if there is an effect, then then maybe this would look better, right? And I was like, sure. So first, we should agree on what the goal of policy evaluation is. I would argue that if you tell me that a policy is X% better than a baseline pi naught, it should be approximately X% better with like high probability, right? So I think we should posit something like saying that it should have a low false positive rate because you're convincing a decision maker. So in this case, it convinced multiple governments and and spent millions of dollars deploying this over thousands and thousands of people. So I want to basically know that if I deploy this, it's going to be helpful and it's going to be a good use of resources, right? So I'm going to define a policy evaluation method as invalid if it does not have a low false positive rate. And in this case, I'm going to try to argue that generally model-based evaluation is invalid. Any thoughts, questions before okay, so let me first say what model-based is. So there's a lot of terminology, so I want to just set up on the same terminology. Something called model-free evaluation. This dates back to Horvitz and Thompson, 1952, although Dean told me there's a 1930s reference, whatever, much before we were born. And so if you do inverse probability weighting on a held-out test set, you get a model-agnostic estimate of how well your policy did, assuming that it's unconfounded and you know the propensities, which in a lot of these papers, that's what they're arguing anyway, because if you don't have that, then you have a lot of other problems in causal inference. The reason that people don't use this method much, at least in practice, that we've seen, and I'll come to a literature survey in a second, is that they have very large variance, especially when the covariates are high dimensional or the action spaces are large. So it actually makes sense that they didn't use this in this particular application because they have 50 cities, and so the action space is going to be very large, and so it has high variance. And so most people in practice actually in the literature use model-based evaluation. So that means they're estimating their counterfactuals using this estimated model. And then they evaluate the policy mostly either using the same function, the same model, or a similar model that's learned from a sample split or a bootstrap sample and so on. I think it's known that this is bad. So why can't I press next? OK, sorry. So it's known for a while that if you use the same function to evaluate your policy, then you're going to get winner's curse, and that's bad. What we are going to show is that even if you learn a slightly different model using a held-out test set or using a bootstrap sample or something like that, you still get the winner's curse problem, and so it is still invalid. You can get arbitrarily large optimistic bias, unwarranted optimistic bias, even when you have kind of all the nice justifications. Okay, so today I'm going to talk about how common model-based evaluation is, because I always feel bad. I love the refugee allocation problem. This is a very impressive kind of work. It's not specific to them. It's like generally in the literature, model-based evaluation happens a lot. And there's many different justifications that are offered, but we are going to show that you still have the winner's curse problem. And then I'm going to argue, okay, so like if we want to do model-free evaluation, because model-based evaluation is invalid, when we know model-free evaluation has very high variance, you might think that we might be able to train better policies that actually get lower variance, and we characterize the Pareto frontier of policies that kind of trade off the average treatment effect and the z-score. Okay, so to understand how common this is and how people justify using model-based evaluation, we identified a sample of 55 management science papers from the last 10 years that do data-driven policy optimization and evaluation. So we did this query on the EBSCO Business Complete database, which if you don't know what it is, I'm happy for you because it's not great to work with. This yielded 875 papers that mentioned data or estimation and optimization or policy in the title or abstract. And then we were like, that's a lot of papers. We don't want to read that. So we fed all the titles and abstracts to GPT 5.2 on high reasoning. And we asked them, is this like an estimate and optimize problem? Is there a policy improvement claim in the abstract? So it's not just like you did a theoretical contribution and you have some random number that you're reporting, but rather you're actually saying for this consequential domain, we can do X% better. Like, is that a headline claim? That brought it down to 111 papers. And then we manually downloaded, and when I say we, I mean Bryce manually downloaded all 111 full texts and read through them. I only went through the 55 that he confirmed as a match. But basically, he was checking for which of them actually have some sort of clear data-driven decision-making pipeline with a clear optimized claim. And then we also wanted to check what are the different methods they use, either in the paper or in the appendix, right? And here's what we found. Only 2 of the papers used model-free evaluation. 53 of them used some sort of invalid model-based evaluation. we're not going to release the papers, but the two, one of them was Dean's papers, so I guess this is a waste of your time. So among the 53 that did model-based, we kind of went in to see what they do. So 35 of them use exactly the same model. So that's like the most pernicious version of the winner's curse that we've known for a long time. And so we wanted to understand like what justification, and then a bunch of them didn't. So like 18 of them did not use, did something that was smarter or more sophisticated. And there were a bunch of justifications given for model-based counterfactuals. Most papers didn't justify it at all. They were just like, here's what we did. But some of them said, hey, the model is really accurate on a held-out test sample. It's very stable. If I take data subsamples, it's well calibrated. And we used a held-out test set. So those are all common things. Very few of them reported any kind of confidence interval. A lot of them use simple parametric statistical models, but some of them are using more complex structural or machine learning models. Okay, just some background. Okay, so if I break down the justifications, they're saying, okay, the model is accurate, stable, and calibrated, and I have random treatment assignment, or I have a well-specified model. If you make either of those claims, it kind of sounds reasonable because my estimated counterfactuals are going to be unbiased, so you might think, that's nice. And then if I also add as a justification 4 that I do sample splitting, then you might think, well, my estimated policy improvement is independent from my pi hat, right, like conditionally independent. And so together I might think, hey, my estimated policy improvement should be valid, right? So it's a very reasonable thing to assume. And what we show is that that's actually not true. And there's two reasons why. One reason is that your model might be misspecified. So like I said, a lot of the models use like a simple parametric model, like a linear model or an MNL model. And if that's the case, it's actually very easy to see why you might still have problems, even if you follow all those assumptions. So let's say that your true function is this solid line. On the x-axis, we have the treatment, and on the y-axis, we have the outcome. We have no covariance, so very simple 1D problem. And let's say, so our true function is this like weird triangle line over here, and you fit a misspecified linear fit, right? That's the dashed line over here. The maximizer of the triangle is the green star, and the maximizer of the dashed line is this red circle, right? And because this function has this large fall off over here, you're going to assume that the true improvement, if you pick it to be at t equals 1, is going to be something like y max, right? So you can take this to be arbitrarily large by scaling y to be very large. So justifications 1, 2, and 4 hold. 3 doesn't hold because it's not well specified. It's misspecified. But this you can take the infinite data limit over here, and so you will always fit this dashed line. So it's accurate, it's stable even under sample splitting. It's fully calibrated, and as t naught goes to 1, your out of sample mean squared error actually goes to 0, while your winner's curve stays constant at y max, right? So if it's misspecified, none of these assumptions are going to help you. And that's intuitively because the optimized decision induces a very different data distribution than what you're observing, right? We have few samples near that t equals 1. And so out of sample mean squared error looks fantastic, but we have very little data over here. Because we took the max, we've gone to like a portion of the covariate space that we really don't have information on. Okay, I think this is sort of obvious that if like misspecification is a problem, you're going to have this, right? The more interesting case is that even if you're not misspecified, so let's say that you say, okay, I'm going to fit a random forest or a gradient boosted machine or something like that, you could still have the same issue, except now it's driven by regularization. I don't have a pretty picture for that because it's like a little bit more of an annoying technical proof. But let's say that all 4 justifications simultaneously hold, and your true model is linear, and your estimated model is perfectly accurate, stable, and calibrated even under sample splitting. You typically will need some regularization to achieve this, so we're going to consider a case where your covariance matrix is a little ill-conditioned, and so you only get accuracy and stability because you regularize. And that's pretty standard because whenever you fit complex non-parametric or richer class of models, you need regularization in order to make sure that you're not overfitting. And if that's the case, the regularization is going to, even if you do sample splitting, you're going to systematically bias the coefficients towards 0 in every low data direction, right? So let's say we only see 4 people from Ukraine. The Ukraine fixed effect coefficient is going to be 0 in the training set and your test set, right? Like that's not going to change, and it's going to be stable as you get to larger sample sizes. So what does that mean? We can show that even as the sample size goes to infinity, your estimated model is arbitrarily accurate. So the out-of-sample mean squared error approaches 0. Stable, so like your sample that you estimate on your training set and whatever you pulled from your bootstrap or sample split, this difference also goes to 0. So your model really, really concentrates tightly. And yet you still suffer an arbitrarily large kind of winner's curse, right? So this isn't to say these are the distributions that we see in real data, but we don't know, right? So this is what I mean by it has a very large false positive rate. And so without being able to bound that in some way, this sort of strategy is invalid. So this was our simulation on the science paper setting, where again, I already showed you that it concentrates around 60%. Now we also took the OR paper where they did a fancier thing. Instead of just looking at it using the same model, they also did this bootstrap evaluation in order to kind of break that conditional dependence due to the winner's curse. And you can see that it still suffers the same issue, that it has a lot of confidence that's well separated from 0. It's much smaller because they took the effort to make sure that the model is stable. But at the end of the day, you're still predicting 20% improvement. That's in a very tight band in a setting where the possible improvement is actually just 0. Exactly. Any questions? Quiet. Okay. No? So what should we do? Okay, so there's been a lot of recent interest in this problem, which I think is fun. So my good friend Vishal has been writing a paper about correcting for this optimistic bias using Stein-based correction. People have also proposed bootstrap-based corrections. There's been interest in selective inference for picking the top K winners. These all still assume that your model is well specified, and at the end of the day, they tell you that the policy you fit maybe is not doing as well as possible. We were really interested in this question of finding better policies, so that I want to actually change how I do policy optimization. And we're really building off of this variance regularization kind of literature. So there's multiple ways you can do this. One way is to regularize the variance in your estimate. So I not only give you the prediction point estimate, but I also give you the standard error around it. And then I try to penalize having too much variance because that's what drives the winner's curse. But you might also do treatment aggregation. You can also do clustering of units. Anything that reduces the dimensionality of the policy class will also help in terms of implementing these model-free methods, right? We wanted to say, okay, so what is the goal? This is sort of ad hoc. We want to specify a specific goal so that we can literally characterize what these policies would look like and how they would qualitatively change as a function of achieving this, right? Okay, so again, our goal is to say, okay, we're going to gather training and test data using some policy. We learn a targeting policy, and then our goal is, let's say, to accept the policy only if it is statistically significantly better than the observational policy, right? So that's what we want to say. We want to say, okay, with confidence 95%, I think this matching policy is better than the random matching policy they're doing right now. And how are we going to evaluate that? We're going to say they're evaluating it on the test data set using IPW. There are other estimators that you can use, but we think this is a good model-free, valid method, right? And so our goal is to learn policies that get this statistically significant improvement. I haven't actually defined IPW, so at this point in the talk, I feel like I should. So why is IPW so bad in terms of variance? Okay, so given a test set where you have your covariates, your treatments, and your outcomes, the treatments here are drawn from some observational policy. And then yn is basically the yn for whatever treatment it was assigned. The IPW estimator for the improvement of your policy is going to be summed over all the samples. The outcomes that you observe in the held out test sample reweighted by the probability that you would allocate that divided by the probability that the observational policy would allocate that. So what does that mean? -1, right? -1 because we're looking at the improvement, not just the estimate of this policy. So why is this high variance? It's because of this ratio right here, right? So this ratio can blow up pretty easily. So if you have an RCT, observational policy will be something like 1/50 if you have 50 treatments, right? So that's already bad. And then pi n t, like normally a deterministic targeting policy will be 1 or 0 everywhere. So you're going to drop a ton of data points where pi n t doesn't match pi observational. And on top of that, the ones where you don't get to drop because they're matching, you get this 1/50 blow up in the variance, or in the standard error. In the variance, you get a 1/50 squared blow up, right? And so that's really the source. But from this expression, you can already see that, let's say that I had a really good estimate for where Marzier will do well, and I have no idea where Dean would do well. Then what I could do is for Marzier, I have my deterministic policy, because I know that I'm going to get really good variance control just from the huge treatment effect. And for Dean, I could just match the observational policy. So if I said pi n t equal to pi n t observational, then this is 1 minus 1 is 0, so it just kind of drops out, right? So generally, making pi n t close to pi n t observational is good because it reduces variance. As we move pi n t farther and farther away from the observational policy, we eat a lot of variance, right? So that's really the key trade-off. So when we started, my intuition was that that's what it would look like for large treatment effects or large signal-to-noise ratio. You would have a deterministic assignment. And for small treatment effects, small signal-to-noise ratio, you would match the observational policy. That intuition is actually not correct, as Bryce told me. So this is an unbiased estimator. Let me show you what it, okay. I'll come back to that thought after I write out the optimization problem. So our optimization problem is to maximize the average treatment effect subject to a z-score constraint, right? So our goal is basically to say, is this policy pi statistically significantly better than the observational policy? Oh, that's not me, okay. At some alpha p, like p-value, right? So like at the 95% level or the 99% level. You can rewrite this as saying it's equivalent to maximizing the average treatment effect subject to a variance constraint on the average treatment effect being less than or equal to beta. And varying beta will give you this Pareto frontier between the average treatment effect and the z-score. Makes sense so far? Okay. So we can characterize the structure of this frontier and show you why my intuition was wrong. I'm only going to talk about the 2-arm case. The k-arm case is messy, but it's in the paper. Okay, so variance regularization kind of looks like this. Before I had this like dashed curve. Now I can regularize the variance and it becomes like this. And then I regularize the variance even more and it becomes even flatter. And you can see that basically the max is still not very well behaved, right? It kind of can go all over the place, right? So this was the max, this red was the max before, now the green, and now the blue. And it's not like it's clear that we're getting closer to the green star, which is the optimum. So it doesn't automatically give you a better solution. It just gives you something that you can evaluate more easily. I'm having so much trouble with this. Okay, so the cool thing we show is that the solutions form a policy that looks like this. So you can ignore the clip. The clip basically makes sure that the probability is actually between 0 and 1. If not, it's not a well-defined probability. But the probability for any zeta is the regularization, sorry, the shadow, zeta is the shadow price for that variance constraint that I showed you below. And it basically says that the optimal policy for any given amount of statistical significance you're targeting is going to be the observational policy plus some little nudge quantity that moves your probabilities away from the observational policy. So when zeta is 0, you get the observational policy back, right? So that's like the most statistically significant you think you can do. It's a little undefined because they're actually then the same policy, so it's not. But as you get arbitrarily close to 0, and as you take zeta to infinity, you're getting the pi hat, the naive kind of plug-in estimator. So it looks like this. So we have pi star of 0 is pi observational. On the y-axis, we have the z-score, and on the x-axis, we have the policy improvement estimate. And then there's a zeta min value at which this grows flatly, and then and this is kind of like a free lunch. So basically what this is saying is that As I shift zeta, for a while, my z-score stays the same, but my treatment effect is actually becoming larger. And so there's really no reason that any of these points would lie on the Pareto frontier, because I can do strictly better at the same statistical significance level. And then after that, we start getting a trade-off. So after that, it's monotonic. So we go from zeta min to zeta max, where we finally hit the plug-in policy. And this is basically a strict trade-off, right? So as we're varying zeta, we're going we're trading off statistical significance for treatment effect or policy improvement, right? So this is basically saying that finding a policy that's better is much easier than finding the best policy, because this is the estimated best policy. This is very hard to do inference on. This is probably much easier to do inference on because the z-score is much higher. But of course, we're taking a hit in terms of the actual performance of the policy. So these are just fundamentally different objects. This object has been studied to death. This object has not really been studied, as far as we know, in kind of any qualitative way. Okay, sorry. And what we find is basically getting higher statistical significance requires random but not uniform treatment. So what's actually happening in this policy when we look at zeta min is that it randomizes allocations to every person. So there's no person where I would say you're going to Philadelphia. Instead, everybody will get some probabilities for going to every possible arm, except for one person. So everyone's allocation is randomized. The moment we make it deterministic for even one person, that's when we start getting the strict trade-off of losing statistical significance. And so inherently, if you want to do well in terms of inference, you need randomized allocations. We shouldn't be learning deterministic policies at all. So the most statistically significant policy, pi star of zeta min, basically becomes this. So it's an indicator, so this is the two-arm case, is an indicator for only one unit. And then for every other unit, we're not saying that we randomize and we match the observational policy. Maybe you're 99% getting arm 1 and 1% getting arm 2, but it doesn't bind to 100% getting arm 1 except for this one person. And then after that, we take a hit in terms of being able to do inference. So anything that's not random for anyone is going to hurt inference ability on a held-out test set if you're using IPW. So let me try to set that. We also thought it was kind of cute. You can write down some closed form functions for what this most statistically significant policy looks like. The average treatment effect ends up being the sum of the signal to noise ratios. The z-score also ends up being a really nice function of the signal to noise ratios. So it has this really nice closed form expression that I thought was kind of nice that you can use to evaluate whether or not you're going to be able to do inference with something in an application. Let me show you how this actually works in practice, right? So we were very lucky that Katie Milkman is my colleague, and she has run this huge mega study that was published in PNAS, I believe, on 680,000 people, where they basically texted people saying, hey, you should get a flu shot, right? So the outcome here is whether or not you're vaccinated, right? Whether you actually get the shot or not. The treatments are different kinds of text messages. So they had 22 different kinds of text messages that they randomized people to. And there were features that were informative, like your age, your health conditions, your zip code, and past vaccinations. This was the same data that's used by Anya and Ron Berman in their paper. So we're just going off of that. And the question was, can we personalize these text messages, right? And so this is basically what it looks like if we actually look at what the model thinks. And again, like I argued, the model is very misleading because it thinks you can do really, really well because you're optimizing against the model. But this is the percentage increase in the vaccination rate that it thinks you can get. And this is on the y-axis, the z-score of your estimate. And we're plotting out this Pareto frontier, right? But if you actually look at your IPW held out test set, it looks a lot worse. So I should say this bottom red line over here is confidence level at a 5% p-value. This red line is confidence level at a 0.01 p-value, so 99% confidence. So here you can see oh, we can do 20% better. There's actually a paper published that said this. You can do 20% better with super high statistical significance. That's a winner's curse estimate. If you actually do it The plug-in estimator is like more 3.5% and not statistically significant even at the 5% level. But it does look like we can get something like a 2% improvement at the 99% significance level, right? So much sadder state of affairs. It's not really clear. I showed this to Katie, and she was like, doesn't sound like it's worth doing any personalization. And I was like, that sounds accurate, at least from what we're seeing. So we can look at these points. So this is the naive estimator. This is the best 95% confident estimator. And this is like the best performing 99% confident estimator. And these policies actually look super different. So the naive estimator is a 100% deterministic treatment assignment, right? So you just say, okay, you get that. You get the best looking policy, right? Arm for you. Once you move to the 95% confident, you're already seeing that half the units are getting a deterministic treatment assignment. The other half are not. They're getting random treatment assignment. And when we look at the 99% point, nobody is getting a deterministic treatment assignment. Actually, one person is, but it rounds down to 0 because we have 680,000 people. But very, very few people are getting deterministic treatments, right? And if we look at the overlap with the observational policy, which was the randomized control trial policy, it's just, we give 1/22 probability to each person. Yeah?
This is a silly question, but can you explain the other points that are above the 99% confidence? Like, why not pick that one? Yeah.
So this point has a smaller treatment effect,
But
right?
It's only a little bit smaller. I mean, don't
Sure.
go all the way, but like, why not pick?
You could pick that. I'm just picking 3. Yeah, this is a great question. Sorry. Yeah, I'm just picking 3 representative points. So obviously you don't want to pick this one. But imagine that your goal is to get the highest treatment effect conditioned with a 95% confidence versus conditioned with a 99% confidence. You might pick this one. Arguably here, you just shouldn't pick any of the points because the effect sizes are too small, sadly. Yeah.
I just had a question about the deterministic treatment assignment. So
Yeah.
I guess I'm not familiar with the exact details of the study, but like, why would treatment not be deterministic? Because isn't it like you just like the pie is just going to tell you, okay, we should do this for this person, or?
This is a great question. Sorry, I rushed through that. Let me go back. I'm just gonna use this. So pi NT is the allocation for unit n of treatment t. So each one is a probability. So this one is, so the only one of these is an indicator. So it would be like pi NT would be like 80% for arm 1 and 20% for arm 2, right?
Intuitively, that makes sense. Slash like a thing that you want to minimize. So like it sometimes makes sense to hedge your bets between two things to minimize errors.
I guess that's true. That sounds accurate. I guess I thought it would be like there would be a signal to noise ratio cutoff, and anything above the signal to noise ratio cutoff, you would get a deterministic assignment, and if not, you would get the observational assignment. And I guess that's like a simple policy, so it made sense in my head. And of course, that's not what it worked out to be. It worked out to be this really annoying thing where like everybody is getting it. So variance-wise, and I don't really understand the intuition for this, but variance-wise, to minimize variance, you're better off nudging everybody. Let's say everybody has the same effect size. Instead of doing 50-50, I nudge everyone to 60-40, and that's better than taking a small percentage of people and giving them arm 1 and giving everybody else arm 2, which a priori was not clear to me, but that just sort of falls out of the form of the IPW estimator. Yeah, does anyone else have any questions? Cool. Okay, so now we can look at the overlap with the observational policy. So the naive policy basically does not the plugin that basically doesn't overlap with the observational policy at all. Where does 4.5% come from? It's basically 1/22. So randomly, because the original policy was randomized, it will overlap with 4.5% by default. This policy overlaps much more with the randomized policy at about 7.5%. And by the time we get to the really confident policy, the overlap is 36%, right? And so basically make sure that everybody is getting closer and closer to the observational policy, and that's how it gets better inference, right? So now we can go back to the refugee simulation environment. So we simulated 3 different conditions. One was with no interaction effects, so that's the one I showed you before where it's impossible to do better because there's no interaction effects between the refugee characteristics and the locations. Next, we tried doing small interaction effects. So there are some small interaction effects, but they might be hard to detect, and so you might find it hard to outperform random assignment. And then the last one we did was we inserted medium interaction effects, so it should be very easy to learn these and outperform random assignment, right? And a priori, we don't know which version of the world we live in, and we basically applied our inference-aware policy optimization approach to all three of these environments. So in the no interaction effect case, again, so this is the 95% confidence level, and this is the 99% confidence level. The X is what the model thinks it's doing. So again, it thinks it's doing super well with very high statistical significance. Again, it's unwarranted. And this is what we get from the held-out test set on Yapo. So we see that basically you might see some like very small effect size, but it's not statistically significant. So it correctly infers that you can't do much here. With a small interaction effect, you can see that the Pareto frontier traced out by inference-aware policy optimization actually does a pretty good job. We find a bunch of points that are significant at the 5% level, and a few that are even significant at the 1% level. Again, the naive plugin estimator, which thinks it's over here, is actually over there. So the naive estimator is doing really badly, and it has no statistical significance at all. We can actually do much better by penalizing the variance, because then we are finding real effects rather than noise, and then we're systematically only using those, right? So you're less likely to overfit and do things that are actually worse than the random policy. And then when you get to the medium interaction effect, then things get a lot easier. So even the plugin estimator is actually significant at the 5% level. Again, it still thinks if you use the model that it's doing way better and it's way more confident. Here it's just barely significant. But the Pareto frontier also traces out a set of policies that actually give you the same treatment effect but are much more statistically confident. So there's really no reason for you to not do this sort of variance penalization. Any questions? Yeah.
This whole idea is for you to like decide what kind of policy to test out. So when you actually recommend it to policymaker, do you recommend this randomized policy, or do you see it as an ultimate pathway where you keep improving your model and ultimately recommending like a deterministic policy?
That's a great question. So I think what we learned from this is that unless you have very low noise, unless you have good variance control, you really should deploy a randomized policy that has other benefits too, because if you are continuing to learn, it will give you a source of, you know the propensities, right? So it gives you a source of information that you can update your model with and then can do continued policy evaluation. And that's actually why a lot of people, so I come from bandits, a lot of times we play a non-stationary bandit, right? Like when we were doing COVID testing, and we thought of that as like an inefficient thing to do where we randomize a little bit, but it gives you information that you can learn from in the future. And so this was kind of interesting to me because I think now it seems like in a lot of these settings where you have this high dimensional policy optimization problem, you actually need to do randomization to control your variance well. And then it also gives you this side benefit of giving you this continuous learning opportunity, right? So I think randomized policies are better. That said, in a lot of settings, maybe you don't have the infrastructure to implement a randomized policy, or there might be other sort of engineering-related concerns. But from a statistical inference standpoint, I mean, like this is, like if I had to choose between this and this, like I'm obviously choosing that point, right?
I just feel like from perspective,
Yeah.
this may feel a little bit too conservative and too rigorous for the statistics' sake. Like some people might prefer just to tell like a compelling story with the naive estimator.
Yeah, I mean, I think that's why the signal-to-noise ratio argument was nice. So the only reason that you would be picking any of these points is because you actually cannot accurately statistically distinguish two different policies, two different arms, right? And so if you can't distinguish it, I don't know that it's conservative, right? Like you have these overlapping confidence intervals, and I guess the naive policy always just picks a slightly higher point estimate. But like the truth is that you don't actually know, and now you can't even collect the data in order to learn. So you've been running this policy that's deterministic for a while. if you go off distribution or there's some non-stationarity, you won't even be able to detect that, right? So I think there's other benefits, but obviously everything comes with pros and cons, so I'm not gonna. Other questions? I mean, the main idea here at the end of the day is that we sort of think about policy optimization, and then inference is this like random thing that pops up at the end, right? And that's what we saw when we were doing the literature survey. Like, people don't give confidence intervals. They don't even really spend any time justifying the way that they're doing evaluation, because inference is sort of like a side thing. The goal is to do optimization, right? But if you actually want to target inference, which is the thing that seems to matter if you're actually going to deploy a policy, then the way you do policy optimization should actually account for that downstream objective. You shouldn't sort of blindly do an optimization and then try to post hoc show that it's statistically significantly better. Okay, so what was the point of me rambling for this long? I'm not really sure. One thing we want to say is that widely used model-based evaluations are invalid because they have these very high false positive rates. So you should, we would argue, use model-free evaluation. And if you are going to do model-free evaluation, you probably want your policy learning to account for that inference task, because if not, you get these really high variances. And so you don't get any statistically significant policy improvement, which is unfortunate for everyone involved. And one of the things we found in this paper is that finding any policy that does better is a much easier task than finding the best policy. So I think typically the intuition is that the best plug-in estimator, like Yuan was saying, is sort of, it would be conservative to do something that's more noisy than that. But it turns out that, establishing that that's better than random treatment assignment is actually much easier. So there's sort of this trade-off. And so we wanted to ask, with limited data, I do a lot of work in healthcare where, like, especially with behavioral health folks at Penn Med. And so they're always running these really, really tiny pilots and these really, really tiny randomized control trials. And then they're like, what can I say from this? Like, what am I powered to say? And typically the answer is nothing, because there's like 200 people and the outcomes are super, super noisy, and there's like 4 arms. And so this paper actually kind of inspired us to do some work with another PhD student, Grace, where we said there's actually a hierarchy of policy learning questions that you can ask. And we actually showed that there are sample complexity gaps between each one. So finding the best policy is the one that's been studied to death. So that's actually the hardest question to answer in terms of inference. The next question is what we kind of talked about a lot today, is that finding any policy that does better than the observational policy, easier question, and you could actually show that the sample complexity gap is like there's a clear gap. But it turns out that another useful question is actually the third one, which I think is really interesting. You can actually say with high probability that there exists a policy that outperforms the observational policy without having any idea what that policy could be, right? So imagine that you have a bunch of overlapping confidence intervals and you can't say anyone is benefited by any treatment, but I can still kind of take a union bound over these and show that there looks like there's systematic heterogeneity across people and across treatments, that there is, with high probability, some policy that's actually better than the randomized policy. But I can't actually tell you based on the 200 data points you've collected which one it is. And this is really nice in kind of the settings that I think about. Because people come and they're like, I ran this small pilot, and I want to know if I should run this big follow-up randomized control trial. Do you think there's enough predictive juice? Should I get an NIH grant for it? And I'm like, I don't know. But now you can actually test for this kind of existence problem so that you can say, okay, it looks like there's probably some value to targeting in this setting versus other problems where there's actually no value. It's actually kind of counterintuitive. Like they ran a study where they gave these pulse oximeters to COVID patients. And there were no heterogeneous treatment effects, and there were actually no treatment effects at all. It was a null effect for the whole treatment, right? So a priori, we might think, oh yeah, that's gonna work. And then a simple thing like gamifying, gamification versus financial incentives on who should wear Fitbits to get them to walk more had pretty large heterogeneous treatment effects, right? So a priori, not intuitive to me anyway. So it's nice to kind of have statistical tests for these. And the easiest question is actually to prove that there's heterogeneous treatment effects. So this is kind of in Anya and Ron's paper, that often just because you have heterogeneous treatment effects doesn't mean that they're actionable, that there is a policy that actually does better than a randomized or baseline policy. There is actually a clear statistical gap here that this is actually a harder question than this. Okay, so I think there's lots of open problems. So doing inference-aware policy optimization across a range of settings. I think I'm out of time, so I'm not going to bother you guys, but do check out Bryce. He's coming to Boston. Yeah.
The observational policy takes on renewed importance because you're going to deploy some version of a perturbation of the observational policy. And that makes me think that you should really carefully choose your observational policy.
Choose your observational policy. Yeah, that's actually a great point. So I guess in some settings it just is what it is. Like in the refugee thing, it was you have some exogenous arrival rate, and you have some exogenous capacity constraints, and so it just is based on their personal relationships and their allocation process. In healthcare, I guess often the observational policy is random, right? Or risk-based or something like that. So I guess I'd always imagine that it's a domain-specific thing that meets some sort of fairness criteria and whatever reality deployment criteria. But that's actually a good point because it actually puts more pressure on that, right? Yeah. Yes.
So I'm new to this. I'm very interested in this. I'm new to this approach. But what I'm struck by is you basically reviewed some large number of papers, peer-reviewed in good journals and so forth.
We hope.
And basically you're saying they're all crap. I mean, no, but
I'm not saying they're crap.
But it's interesting to me because very often we get, I'm not pointing to any particular person, but there's an optimization that we can do something.
Yeah.
But it's not really understanding what's happening. So I see all kinds of things where we're trying to optimize some kind of value for a decision, but we don't really know how to measure decisions. So we maybe come to some financial criteria, but doesn't measure the other things that matter. That might be the risk amount or the equity or various other things. So it's amazing to me structurally how a field can be focused on large numbers of papers, which in some ways, as I can believe, are basically pointless. No, I mean, but seriously, we get trapped in a method which leads us to something that looks good. I see it in my own field, which is different, but it looks good, but in fact, isn't.
I think
comment on that kind of thing.
I think Dean has a better answer to this than I do.
I did it right.
What? Yeah, you did it right.
I mean, I guess maybe a follow-up question is to what degree were these papers really focused on that kind of headline policy evaluation number, and
your point
what part
earlier,
of the contribution of that?
So during our one-on-one, I guess Dean made this very insightful comment. I thought that these communities emerge sort of separately. Causal inference has been its own sub-community, and then these more data-driven optimization problems have been a different community, and so there hasn't been a bridge that was built. And to your point, they're more focused on the optimization. Like I said, most of them don't even talk about the inference. There's no confidence interval. Only very few of them reported any kind of inference strategy. That said, we only looked at papers that claimed an improvement in the abstract. So I think we don't look at any papers that kind of just say, oh, there's an improvement and it's just a simulation, right?
It seems interesting for how we think about things, that we have these communities which are full of bright people doing supposedly great work, but they don't really understand the problem in some more fundamental way. So they're not talking about these kind of things.
I think what I've learned in my own experience is that I've done a lot of stupid things because interdisciplinary work is hard, right? So this kind of project, for example, they have to understand political science. They have to talk to government stakeholders about how to match these things. They have to understand qualitative science to interview people at the refugee matching point to understand what their constraints are. It was a huge, very impressive effort. And then on top of that, they also have to understand machine learning, optimization, and causal inference. And that's just a huge ask, right? And I don't even know that academia philosophically rewards that kind of a massive effort. And so it's very easy to come afterwards and be like, well, you did it wrong or whatever. But I think it would be better if, like, as a community, we had sort of built on that problem and different perspectives had been integrated from the start, and then we wouldn't have gotten to this point, right? Like, if more causal inference people were working on this problem, like, Dean, if you had worked on this problem, everything would have been fine. So it's really your fault.
Not that specific point, but the broader message that you had, I thought was a really great place to end this for IDSS in particular, both highlighting how hard the interdisciplinary work is that a lot of us are doing, and how needed some of that combination of expertise is. So it was really a pleasure to have you, Hamsa. I think maybe she could take a couple more questions, but probably you're about to run off to get home.
Yeah.
So thank you so much.
Thank you, guys.